This is part 2 of our lecture on substitution. We're going to jump straight into some follow-up examples that are getting kind to be of moderate difficulty. All right, in part 1, we addressed some basic examples. We saw the idea of manipulating differentials come up in a few of them. And we're going to take a look at an example 3, or ones that might require some other ideas. So I'd like you to make an attempt at these, just to give some hints. Just be careful with maybe trying to rewrite some of them first. It might be written in kind of a non-obvious way of how to approach the problem, but see if for some of them you might be able to rewrite it. We'll check in a few minutes. All 3 of these require substitution. We'll check in a few minutes. All right, welcome back. Let's go through part A. This one might be a little bit trickier to deal with fractions. There's not really an apparent inside or inner function inside of fractions. There's the numerator and denominator. But let's keep the idea now of what we choose for u. We would want its derivative, du, to be a factor. Now here, if we choose u as x squared plus 1, the derivative of x squared gives us a factor of x in the derivative. And that's exactly what we have in the numerator, a factor of x. So if we choose u as x squared plus 1, the differential du is 2x dx. And we have a factor of x dx in our integral, but not 2x dx. No problem, we divide the 2 over to get a factor of a half in the differential, and we can rewrite our integral now, x dx as 1/2 du, and then the remaining fraction, 1, divided by x squared plus 1 squared, we can rewrite that as 1 divided by u squared. Now this can be expressed as a basic antiderivative. If you rewrite 1 over u squared as u to the negative 2, this is now something we can integrate using the basic power rule for antiderivatives. Add 1 to the exponent, and then divide by the new power. All right, we can express that antiderivative. Instead of u to the negative 1, you can rewrite it as 1 over u. And if you plug in your u as x squared plus 1 from what we chose, we get our antiderivative in terms of x. All right, hopefully this one went well. Part B is a little trickier. Part B, a hint here was to try to rewrite it. And our first step is to think, well, how might we rewrite tangent of x? There's not a lot of obvious identities, but one that certainly should come to mind is that tangent of x is sine of x divided by cosine of x. If we rewrite tangent of x as that, now notice if we choose u as the denominator, u as cosine, the derivative of cosine contains a factor of sine of x, which is exactly what's a factor in the numerator of our integral, sine of x. So it looks like our substitution u as cosine of x will work. The differential du is negative sine of x dx. We have sine of x dx as a factor in our integral, but we're just missing that negative. So divide the negative over in the differential statement, and we get negative du equals sine of x dx. We can then rewrite the whole integral, the cosine of x in the denominator. We can just replace that with u, and we get a very simple antiderivative, or integral, the integral of negative 1 over u du. Now, this function, 1 over a variable, usually 1 over x, but now 1 over u, the antiderivative is natural log of that variable. The negative just stays as a constant multiple, so we get as our antiderivative negative natural log of u. We can back substitute u as cosine of x, so we get our first version for the answer as negative natural log of cosine of x. Now this is an acceptable answer, but if you're checking other resources, you might have encountered a different answer, natural log of secant x. So let's see how that might come about. This uses properties of logarithms, which hopefully you haven't forgotten. The version or property we're going to use is the version that relates exponents or powers inside to factors out front. So natural log of a raised to the nth power is equivalent to that exponent coming down as a factor n and then multiplying natural log of a. How we can apply that property is we're going to take the factor out front, -1, we bring that up inside to get a power of -1. So our antiderivative, we could express it as natural log of cosine of x to the negative first power. Be careful, this is not notation for inverse cosine, but cosine of x raised to the -1. And recall how we interpret a negative first power. We can interpret that as 1 over that quantity. So cosine of x to the negative first power, that we can rewrite as 1 over cosine of x. 1 over cosine of x is equivalent to secant of x. So we can rewrite this whole answer, our antiderivative, as natural log of secant of x. Both answers are fine. You don't have to convert and rewrite as we did here. That's just to explain how you might be able to take one antiderivative and express it as another. All right, let's move on to part C. This is a good one. There's going to be a few different ways that we can answer this. One way you might have approached this is trying u as sine of x. And as it turns out, that works. If you choose u as sine of x, its derivative, cosine of x, is a factor in the integral. So this is a very simple u substitution problem. You get as your integral, the integral of u du, and we can just integrate that using the power rule. We get 1/2 u squared plus a constant, and then we plug our u back in. U was sine of x, so we get our antiderivative as 1/2 sine squared of x plus a constant. Now, this is not the only way to answer this question. You could have done this with a different substitution. Instead of choosing your u as sine of x, it's completely correct also to choose u as cosine of x. It's a little more complicated due to the negative that pops up in calculating the differential, the derivative of cosine, but it's pretty much the same thing without that factor of a negative from above. So we choose u as cosine of x, du is then negative sine of x dx, manipulate the differential, divide the negative over, and we get the integral of negative u du. Very similar to above, but there's now a crucial difference, the negative sign. Our antiderivative would then be negative 1/2 u squared plus a constant. So we immediately get a different looking answer, negative 1/2 of cosine squared plus a constant. Now these answers for the antiderivatives look different, but are they really? They certainly look different, but trig functions in particular have a whole bunch of identities that allow you to rewrite one expression in several different forms. So let's think what identities might be relevant to squared trig functions. Well, the Pythagorean identity. The standard one, or basic one that I think every calculus student recalls, is sine squared plus cosine squared equals 1. Now, with this, you might be comfortable using the kind of alternate versions, solving individually for sine squared and cosine squared, so just subtracting. And if we use this manipulated version of the basic Pythagorean identity, we can convert one of these antiderivatives to the other. So let's convert the 1/2 sine squared antiderivative to the one that we found in the second approach. All right, so if we take our antiderivative from the first way to answer this, 1/2 sine squared plus a constant, c, we can replace sine squared with its Pythagorean identity, sine squared equals 1 minus cosine squared of x. We can distribute that 1/2 through parentheses. What we have is now 1/2 minus 1/2 cosine squared plus c. How do we make this look exactly like the antiderivative we found in our second approach? Well, c is a constant. We're adding to c another constant, 1/2. 1/2 plus a constant is just another constant. Let's call that other constant d. And what we have now is an equivalent version for the antiderivative, negative 1/2 cosine squared of x plus a constant d. That is the same. The name of the constant doesn't matter. So earlier we had it as plus c, but here plus d. We just proved these antiderivatives, these answers are the same. So all is well. Different approaches, different ways to solve problems in mathematics should lead to the same answer. So fortunately it worked out. All right, now as it turns out, there's not two ways to approach this. There is a third way, but it's kind of not as obvious. We're starting to introduce some trig identities here. You might keep in mind some important trig identities that you maybe know, but chances are you don't. There is a third approach using the double angle identity. The double angle identity we're going to use is sine of 2x equals 2 sine of x times cosine of x. Our integral here was an integral for sine of x cosine of x. And let's go ahead and actually integrate that by first rewriting it. So we can rewrite our original integral of sine of x cosine of x using this double angle identity. We can rewrite it as 1/2 sine of 2x. And then we can apply what we introduced at the end of the first part of this lecture with the 1/a shortcut. We know a basic antiderivative for sine. The inner expression, 2x, is linear of the form ax plus b. A is 2. So when we integrate, we get another factor of 1/2. And then the antiderivative for sine is negative cosine. So this one is a little trickier since it requires you to be familiar with the double angle identity, but it is a third different approach. All right, let's go ahead and get to some other examples. These ones are probably the hardest of all. I'd like you to make an attempt at these. The first one, part A, I'll give you a hint. Previously, we set up the idea of manipulating the differential. Part A here of example 4, maybe try manipulating the substitution. Remember, your goal with substitution is to convert everything from an x statement for an integral, where x is the variable, to an integral involving u. So a hint for part A, try to manipulate the substitution. We'll check in a few minutes. For the other ones, parts B and C are definitely fairly challenging. All right, welcome back. Let's go through part A. Here we have hopefully an obvious inner expression, u equals 2x minus 1. So we'll try that as our u. We can calculate the differential du as 2 dx. From examples we've covered, no surprise that we might have to manipulate the differential here. So we're solving for dx to get 1/2 du equals dx. But what's tricky here is converting that factor of x that's by itself. Now keep in mind, you want to convert everything from x to u. How might we convert x and express that as u? Well, we've set up the idea of manipulating the differential, we can also manipulate the substitution. So we can take our substitution, u equals 2x minus 1. We can solve that for x. Add 1, then divide by 2. This now allows me to kind of replace x by itself in terms of u. Now we can convert all three pieces, the factor of x, the square root expression, and the differential dx. We can convert all three pieces in terms of u. If we plug in, instead of dividing by 2, I'll think of x as being 1/2 u plus 1. We then have that square root expression becoming square root of u, and then the differential gives us a factor of 1/2. To solve this, we can distribute, think of u as u to the 1/2 power, or sorry, the square root of u as u to the 1/2 power. And if you distribute that in, multiply the same bases, you can add the exponents. So if you multiply, you should get, before integrating, 1/4, and then the function by distributing is u to the 3/2 plus u to the 1/2. And then each of those terms we can integrate using the power rule. Add 1 to the exponent, and then divide by the new power. Notice we're already incorporating dealing with radicals. When we apply the power rule, divide by the new exponent, we're multiplying by the reciprocal here. Hopefully you've started to incorporate that as well. All right, so we get as our antiderivative 1/10 u to the 5/2 power plus a 6th u to the 3/2 power, and we just back substitute u as what we chose. U was 2x minus 1. All right, now this one sets up the idea of manipulating the substitution in addition to manipulating the differential. All right, let's take a look at part B. This one, if you were stuck, maybe pause the video from here and make a second attempt. I'll give you a hint. At some point through this problem, you need to recall this basic antiderivative, which comes from a basic derivative. The integral or antiderivative of 1 divided by 1 plus x squared is inverse tangent. That's because the derivative of inverse tangent of x, from what you learned in the kind of middle point of your Calc 1 course, that derivative of inverse tangent is 1 divided by 1 plus x squared. So maybe pause the video again and see if you can use that as a hint. We'll check in about a minute. All right, now I realize this tip by itself may not be enough of a hint, so let's try to give some others, how we're going to go from the existing problem to make use of this. All right, if you were to try maybe your obvious choice, let's go with u as the denominator, 1 plus x to the 4th. Think of what the derivative of x to the 4th is, 4x cubed. We have a factor of x by itself in the numerator, not x cubed. So this choice of u, its derivative, doesn't seem to work. All right, now let's maybe work backwards. Let's think maybe, that factor of x, maybe it's used with dx. So let's try to think what x dx might correspond to. All right, that might be the differential. Now, what would give the differential basically as x dx? Well, if the derivative or differential has an x in it, the substitution must have had an x squared in it. So kind of thinking backwards a little bit differently here, this is pointing to us maybe trying u as x squared, since the derivative of x squared is 2x. The factor of 2 doesn't make a difference, but the factor of x does, which is what we have in the numerator. Now, how do we actually incorporate this idea of trying the substitution u equals x squared with this hint about using the antiderivative of 1 over 1 plus x squared being inverse tangent? Well, let's go ahead and rewrite x to the fourth in the denominator as x squared squared. Now you might be able to see where or why that substitution u equals x squared comes in. If we choose u as x squared, du becomes 2x dx, and we can solve for x dx, divide that factor of 2 over as 1/2 du equals x dx. Now if you use your substitution and differential to rewrite that rewritten integral, we rewrote the denominator as 1 plus x squared squared. The part inside parentheses we can replace with u. We convert this entirely to u. We get 1/2 times 1 divided by 1 plus u squared du. And aside from that factor of 1/2, this is the basic function that has inverse tangent as its antiderivative. We have it stated in the upper right corner where x is the variable. We have it as the integral of 1 divided by 1 plus x squared dx. But here, midway through the problem, we have it as the integral involving 1 divided by 1 plus u squared du. So we make use of that basic antiderivative. Here we get it as inverse tangent of u instead of inverse tangent of x. All right, the factor of 1/2 stays as a constant multiple, and we complete the problem back substituting u as our substitution, which was x squared. So we get our antiderivative as 1/2 inverse tangent of x squared. Now this one is certainly probably tricky, especially if you kind of didn't recall what the basic derivative of inverse tangent was, which we reversed to give us now this basic antiderivative. So definitely go back and familiarize yourself with basic antiderivatives, especially these ones that give inverse trig functions as answers. All right, let's take a look at part C. This is the kind of trickiest one of all. This one involves basically a combination of everything. We're going to take as our starting place, notice we have a square root expression. Let's go with the inner expression or inner function, 1 plus x cubed as our u. So if we choose u as 1 plus x cubed, we get the differential du as 3x squared dx. And we manipulate that, divide the 3 over to get the statement 1/3 du equals x squared dx. Now, how do we actually incorporate that with the problem? We have a factor of x to the 5th in the integral. Well, let's split up x to the 5th as x cubed times x squared. If we put that x squared factor at the end, we can now rewrite x squared dx as 1/3 du. That factor in front in the integral of x cubed, which we got by splitting up x to the 5th, we can express x cubed as u minus 1, manipulating the substitution. So if we use a combination of manipulating the substitution and manipulating the differential, we can rewrite all these pieces in order. X cubed converts to u minus 1, the square root converts to square root of u, and x squared dx converts to 1/3 du. Definitely tricky since it involves a little bit of everything, but it's enough for us to complete the problem. Very similar to our introductory example dealing with radicals. We can kind of go ahead and kind of express everything as powers of u, rewrite the square root of u as u to the 1/2, and then distribute that in, and it's virtually the same calculation as what we did earlier, just with some different factors. So at the end here, integrating u to the 3/2 and u to the 1/2 power, we just apply the basic power rule for antiderivatives. And then at the end there, back substitute u as 1 plus x cubed. All right, this was definitely the trickiest of all. hopefully through all the examples, example 1, 2, and then up to now this multi-part example, hopefully you start to get a sense for how substitution is used and the different ways you can be a little bit creative with it through manipulating the differential and most recently manipulating the substitution. All right, now before we move on to some final ideas, for instance, we haven't talked yet about definite integrals, so limits on the integral sign with substitution. We'll be getting to that. Let's take the time to take a look at an important formula that we'll be using later in the course. We'll recall this formula when we need it, but with substitution available to us now we can kind of prove it if you want to. All right, in example 4b, we made use of the integral of 1 divided by 1 plus x squared, coming out to being inverse tangent of x. All right, what we're going to need for later is an integral formula where in the denominator it's not 1 plus x squared or x squared plus 1, reversing the order of addition, but it may be x squared plus a different number. So here we have it written generally as 1 divided by x squared plus a squared, where a is a constant. Now there's several ways you can prove this. One way is using u substitution. If you choose an appropriate substitution, you get as the antiderivative for 1 divided by x squared plus a squared as 1 over a times inverse tangent of x over a. Now, a way that you can prove that using substitution, I'll leave the details for you to work out. This one's a good problem to try. Try the substitution u equals x divided by a. Try to make that work, and what you should get as your final answer, the antiderivative, you should get 1 over a times inverse tangent of x divided by a. We're going to use that later in the course. We'll recall this formula when needed. All right, now all the examples so far, I like to kind of get all the ways we use and choose the substitution out of the way first, saving definite integrals, integrals where there's limits, a and b on the integral sign, for last. The presence of limits really doesn't complicate anything. It's in fact very minor. It has no effect or influence on how we choose u. It's just basically an extra step, as we'll point out. All right, like most places in mathematics, there's several ways you can approach it. One thing I want you to look at for this definite integral is there are 3 quantities that appear in this, and 3 quantities that you might think of from what we've looked at in previous examples in this lecture and examples. All right, the 3 quantities here, first is f of x. That's the function that we're basically integrating. Through previous examples in this lecture, we've manipulated the differential dx. So think of dx as being a quantity in this integral. And then a third quantity, it's what a and b represent, the endpoints of the interval from a to b. So this definite integral has 3 pieces, ingredients or quantities that go into defining it: the function, the differential, and the interval. We were emphasizing substitution converts from an x integral to a u integral. I'd like you to think for a definite integral, you're going to now convert all 3 quantities. You convert the function, you convert the differential, and convert the limits. This approach leads you down to some ideas you might be encountering in multivariable calculus, but we'll save that for Calc 3 if and when you reach that. All right, let's go ahead and approach an example using this idea of converting all 3 pieces. Again, the presence of limits has no effect on how you choose your substitution u. Here, since we have the function 2x plus 1 raised to the 5th power, look at that as being 2x plus 1 is inside the 5th power. So we can choose u as 2x plus 1. Hopefully that's pretty obvious through all the examples we worked through. With our choice for u, we still calculate the differential. Here, du comes out to 2 dx. And since our integral doesn't have a factor of 2 in it, there's just dx, we manipulate the differential by dividing the 2 over to get the differential statement 1/2 du equals dx. That's all old stuff through what we've covered through the examples in part 1 and part 2 of this lecture. Now, what do we do with the limits? The approach I advocate is we're going to use the substitution to convert from x limits, or the original limits, to new limits for u. It's really simple. We just take our substitution here, u equals 2x plus 1. We chose that. And we just plug in those x values, or limits for x. We plug in x is 2. Plug that into your substitution, 2 times 2 plus 1. We get the corresponding upper limit now for u converts to 5. If you plug in x as 0, your substitution gives you u equals 1. So this is how we're going to convert the limits, which really is very minor. It's just plugging in your original x limits to the substitution to get converted u limits. Now, if we use all the ideas with rewriting the function, manipulating the differential, and now converting the limits, we can easily answer this problem without going backwards and back substituting. We can rewrite our integral now as the integral from the new limits 1 to 5. 1 to 5 corresponds to the u limits. 0 to 2 corresponds to the original x limits. And then everything else converts. We get now our integral of 1/2 u to the 5th du. This we can apply the basic power rule. We get an extra factor of 6 in the denominator. Our antiderivative, we can express it as 1/12 times u to the 6th. And then we evaluate that with the new u limits. This is the benefit of converting the limits. We don't have to back substitute u in terms of x. We can just keep going forwards and use the new u limits. And if you plug in u is 5 and subtract, when you plug in u as 1, you get this rather large number. It's actually simpler, in my opinion, to leave this as 1/12 times 5 to the 6 minus 1. It's a pretty large number. This is a little more aesthetically pleasing, in my opinion. All right, now just in case you did want to convert your u back to x, if you plug your u substitution back in, you have to use the original x limits. So these are two different approaches. Either choose your u and convert your limits, or with your choice for u, plug your substitution back in and use the original x limits. If you do that, with the second approach, convert u back to x, replace u in u to the 6 with 2x plus 1, and now we use the original x limits 0 to 2. It's still plugging in. You get the same result either way. The benefit of converting the limits is you never have to refer to your u substitution again. So throughout the remainder of the course, and any place that you encounter substitution with definite integrals, I'll always advocate for the converting the limits approach by using the substitution. All right, that is pretty much it. I feel like we've covered a lot of examples. There's going to be some examples dealing with definite integrals. Try the converting the limits approach as we're looking at here. But I want to take a look at another property of integrals that we can actually have a simple way to prove now. And this is a relationship with definite integrals for functions that might be even or odd. So let's review the even and odd properties. If a function is even, its graph is symmetric over the y-axis. If a function is odd, we say the graph is symmetric through the origin. Even symmetry is a single or one-fold symmetry. Odd symmetry is a two-fold symmetry, a simultaneous reflection over the y-axis and x-axis together. Now, what the even and odd properties allow us to do is, let's say we have a function, this is part one, we're going to say the function f is even, and the interval is a symmetric interval. It's symmetric around 0. It's an interval from a negative number to the positive number. Here we have the interval negative a to a. If your function's even and the integral is over a symmetric interval, you can basically double the integral or area from 0 to a due to symmetry. Notice with respect to that symmetry over the y-axis, the region on the left, it's the same size as the region on the right side of the y-axis. So why not just double the region and area on the right? And that's what the even property amounts to. Now for odd functions, this is even better. If you have the integral of an odd function over a symmetric interval, the integral, definite integral, evaluates to 0. Why is that? Well, take a look at the regions there. On the right, you have the region above the x-axis exhibiting positive area. The region on the left below the x-axis refers to and exhibits negative area. This is the idea of net signed area. Those regions are the same size, but one's positive and one's negative. They cancel out, giving you this definite integral over a symmetric interval as being 0. Now, I like to bring this up at the end once I've introduced substitution in a course, since substitution is, in my opinion, the simplest way to prove these properties of integrals. We're going to make use of it through the remainder of the course. It's used throughout the rest of the calc sequence. I wanted to make sure you see logically how substitution is used to prove these. Give that a try. Try to use some properties of integrals with substitution to prove these. We'll take a look at other ideas later in the course.